Hello, I'm Jack. Welcome to my channel, Practical Programming with Dr. Su. In this video series, you will learn everything you need to get started with wgpu graphics programming in Rust. In the last few videos, I explained how to create some simple 3D shapes. However, when rendering these graphics objects with solid colors, you may find that the image looks flat and is failed to illustrate the 3D nature of the object. This is because we neglected the interaction between light and surfaces in our objects. Lighting helps provide visual effect to a scene so that it looks more realistic. In fact, the lighting is one of the most important factors for creating real-world shaded 3D graphics objects. However, wgpu does not have much built-in feature on lighting. It just runs two functions, vertex and fragment shaders. If you want the lighting effect in your 3D scene, you have to create a lighting model yourself. In this video, I will show you how to build a simple lighting model in wgpu and how to use it to simulate the light source. Here we will discuss three types of lighting source: ambient light, diffuse light, and specular light. The ambient light is the light that illuminates all objects uniformly, regardless of their location or orientation. It is a global illumination in an environment. The diffuse light and specular light depend on the angle of the light to a surface. Here is diffuse light. When the light hits the surface, the diffuse reflection occurs in all directions, as shown here, while the specular light occurs in a single angle here. Here shows the light in reflections on a torus surface. On the left here, from the ambient light source only, you can see it's flat. At the center shows the light effect from both ambient and diffuse light, while on the right is the light effect from ambient, diffuse, and specular light sources. You can see that the torus with only ambient light looks flat. The torus with the diffuse light has a 3D effect. The torus with the specular light looks more realistic. You can see here. The light reflection depends on the angle at which the light hits the surface. The angle is essential to the diffuse light and the specular light. This angle is always associated with the surface normal that is perpendicular to the surface. Once we have calculated the normal vector at our vertex, we can use it and the direction of the light to compute the lighting intensity. For diffuse light, its intensity is proportional to the cosine between the light vector and the normal vector. Here alpha is cosine alpha equal to normalize the L dot product in the normal vector. ID diffuse intensity, and KD is diffusion material property. So we can have this relation ID equal to KD times maxima cosine alpha and 0. Here the maxima function is used to avoid the negative value of the cosine alpha here. We can also add the ambient light to the diffuse light intensity, like this. So we have this IA is ambient intensity, so we can add to the diffuse intensity like this. For the specular light, we have two models. One is a fun model. This model is very simple. For example, IS is specular intensity, KS specular material property, S is thinniness of the surface or roughness of the surface. So here intensity IS equal to KS times V dot R. V is the view direction, R is the reflection direction. So we have this relationship. The issue with the fun model is that the angle between the view direction and the reflection direction has to be less than 90 degrees for the specular fun term to contribute. Otherwise, this dot product will be negative. It's not valid. So in order to avoid this difficulty, we can use the Blaine fun model to address this issue. This model uses a different set of vectors for its computation based on the half angle vectors. Here is L, light direction. The N is normal vector N. The V is view direction. And H is half angle vector. So his definition is L plus V. L is light direction plus V direction. So we get the H. So normalized by the length of L plus V here. So here we use N, the normal vector, dot H, the half angle vector, instead of V dot R here in the fun model. So Blaine fun model use different set of vectors to have this term. It's N times H. You can see here N and H, the angle between these two vectors always less than 90 degrees. In this video, we will use the Blaine fun model to calculate the light. Okay, let's go to the programming part. Again, we will use the gate tool to clone the source code used in the last example, and then make some changes to that source code to build the project used in this video. Now, let's start Visual Studio Code directly from Windows Start menu. Click this Visual Studio Code. This is Visual Studio Code interface. Now let's start a new terminal window and cd into code. Here let's make a new folder called wgpu09 and cd into it. In this folder, we can clone the source code used in the last video with the command git clone wgpu08. After this command, leave a space and a period. This will place our source code in the current folder. Now run this command. Okay, we can check use direct. You can see the source code is indeed in the current folder. Now we can open this folder from Visual Studio Code. Open folder, code, wgpu09. Here contains the source code used in the last video. Let's implement the light model in the seeder code from src folder. Open the seeder.wgsl file. Now we need to replace its content with the new code. Right now, the seeder code becomes more complicated because we need to implement the light model in the seeder. Here you can see we pass three uniform matrices here. One is model matrix, view projection matrix, and the normal matrix. Here the normal matrix is the transformation matrix for the normal vector data. When applying a transform to a surface, we need to derive normal vectors for the resulting surface from the original normal vectors. If we make a non-uniform scaling transform to the surface, the transformation to the normal vector need a special consideration. In order to transform the normal vector correctly, we don't simply multiply them by the same matrix used to transform our object, but we need to multiply them by the transform of the inverse of that matrix. Since WGSL does not implement the matrix inverse function yet, so we have to make this transpose of the inverse of transformation matrix in Rust, and then pass it as a uniform matrix as shown here. This normal matrix here is a uniform parameter passed to this seed code. We then define an output structure here that contains three fields. One is built-in position, another is V position, and another one is V normal. This is the vertex data for position. This is for the normal vector data. Inside this VS main function, we only perform model transformation on the V position. You can see V position because it is used in the light calculation. You can see here we perform the normal matrix times the original normal data. Here the V position and V normal vectors will be passed to the fragment seeder to calculate the light model. So the default position is obtained by perform the model view and the projection transform on the vertex position data. In the fragment seeder, we define two uniform structures. One is called frag uniforms, and the other one called light uniforms. The fragment uniforms here is used to pass the light position and I position, while we use the light uniform structure to pass the parameters for the light calculation. The fs main function here takes V position and V normal from vertex seeder as its input arguments. Inside this fs main function, we calculate the light model. Here we start with define various vectors, including the normal vector here. This is derived from V normal. It's x, y, z. So we define the normal vector, use this relation, and then we define the light direction L vector, use this relation, and then view direction. Next is half angle. Half angle is L plus V. We have already explained these vectors, so you can see diffuse light is N dot L. We use the plane form model to calculate the specular light. You can see here we use half angle N dot H. So ambient light is added to the diffuse light as a constant here. The output color from the fragment seeder will be weighted by the light intensity from the ambient, diffuse, and specular light sources. This is the seeder we will use for calculating the light model. Now we can save this file and close it. Next, in the src folder, we will add a Rust file called common.rs. Add a new file. And then we need to add some code to this file. Here we first define a light structure. You can see the light structure. This structure contains several fields including color, specular color, ambient intensity, and other fields, which will be used for the light calculations. And then we implement a function called light here. This function accepts the color here C and specular color SC is F32 3 type, and we want to convert them into F32 4 types. You can see color, we add 1.0 to the alpha channel, and specular color also add to the alpha channel with 1.0, which can be used for the light computations in the CIDR. Next, we define vertex structure. You can see the vertex structure contains two components. One is position, one is normal. We then use the vertex attribute array, and this is a macro to write an implementation block for the vertex structure that create a static method called DESC, means description, which returns a vertex buffer layout. You can see this return vertex buffer layout. Note here, we then pack all the fields required for drawing our graphics shape into another structure here called state. We implement this state on the structure. You can see here within the state implementation, here the new function is the async function. This function accepts vertex data and light data as its input arguments that will be provided by the user. In the uniform data section, we create a view and projection matrix by calling the transforms create a view projection methods. We then create a vertex uniform buffer here using the device create a buffer function. This allows you to set the buffer size and offset. Buffer size here we use 192. In our current example, vertex uniform buffer will store three 4x4 matrix, including the model matrix, a view projection matrix, and a normal matrix. Each matrix is 4x4, so each matrix needs 64 bytes of memory to store its data. So the total, the three matrix, the size will be 3 times 64. That's y equals to 192. Since these matrices will change through either a rotation animation or a window resize, we will write this data to the vertex uniform buffer inside the update function. Next, we create a fragment uniform buffer that stores a light position and eye position. The light position and the eye position will not change with rotation animation or window resize, so we can store them immediately after create the buffer. So we immediately write here, not inside the update function. Next, we create a light uniform buffer. We also write the light parameters directly to the buffer because these parameters don't change with the animation. So we directly write his data light data into this lighting uniform buffer. We then create a uniform binding group layout and a uniform binding group whose entry attribute contains three elements with the binding. You can see one is at 0, another one at 1, final one is at 2, which corresponding to the vertex uniform buffer here at 0, at 1 is corresponding the fragment uniform buffer, finally at 2 is the light uniform buffer. So we have three uniform buffers. So you can see here at binding 0 we have vertex uniform buffer. At binding 1 we have fragment uniform buffer. At binding 2, we have light uniform buffer. Remember that in our seeder code, we use the binding group and binding location to access data stored in different buffers. Next, inside this update function, here, we set a rotation animation with a time duration. You can see this translation, this rotation, this is scaling. So here we use dt here, time variable, to define the rotation as we did in the last video for animate the cube, which is passed to the model matrix here. We then create a view projection matrix. Next, we create the normal matrix. You can see how we did it. So by inverting the transpose the model matrix. We don't use the model matrix directly, so we have to perform invert first, then transpose. Then we get a normal matrix. Finally, we write the model view projection and the normal matrix to the vertex uniform buffer. You can see here. First, we write the vertex uniform buffer at offset 0, and then we write this model matrix, and then view projection matrix at offset 64. And finally, we write normal matrix to this vertex uniform buffer at offset 128. In order to avoid the code duplication, we also convert the content usually found in the main function into a new run function here. The rest of the code is the same as that used in the example presented in the last video. Now we can save this file and close it. Up to now, we have completed this application. In next video, we will use this light model to create some 3D graphics object. Thank you for watching.